Hello everyone, welcome back to another chemistry video. So exciting, I know. um, so this is going to be about trends on the periodic table to kind of help streamline some of this and some other stuff. So first, let's talk about electron configuration. Oh, look, I have colored pens. Okay, so we know that there are four sublevels, or S, P, D, and F. But based on the periodic table, we can kind of get some trends so you don't have to write out the rule of diagonals every time, which is great. So we have four blocks. So this blue block I'm highlighting, which also includes helium. This is our S block. And so the S block, in our S block, little S block, these are going to be the elements that their last thing in the configuration is going to be an S. So this group right here is going to be end on a 1. And this group right here, remember helium's here, is going to end on a 2. And then so this is going to be like 1s1, 2s1, 2s2, 3, 4, 5, 6, 7. So that's the S block. This block right here, that is our P block. So all of these are going to end on P. But remember, there's no 1P. So you have to start on 2. So 2, 3, 4, 5, 6, 7. And then this is going to be 1, 2, 3, 4, 5, 6. All right, and helium 6. So say, aluminum is going to be 2p1. Oxygen is going to be 2p4. Then, let's go purple. This middle block, our transition metals, minus our little lanthanoids. Let's choose their color. They can be green. Green, green, green. Okay. So, let's do the transition metals first, though. So, our transition metals, that is our D block. And remember, the D's don't start till 3. So 3, 4, 5, 6. See, there's no 7. And then this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But what you need to look out for is 4 and 9. So this block here, which I think is chromium, and this block here, which zinc maybe, copper, silver, gold are all in here. So these are going to be different because they are going to fill up their D block, or they're going to say you have chromium, it's going to be, let me just show you. So chromium has 24 electrons. Okay, 24 electrons. And Cr, so say we do noble gas, it's argon. So what you would think is that this would be 4s2, 3d4. Well, having a half-filled D level is more stable than having 4, so it's actually going to be 4s1, 3d5. And then the same for copper, and anything down this line, all of this, all of these are going to be that. So this is going to be your half-filled D. This is going to be your full D. And this is going to be, I don't think, this is also argon. And this is going to be 4s1, 3d10. So that's just something to remember. So that's the exception to the rule you want to remember so you don't get that wrong. you'd get it wrong with the electron. You just got to remember this. This is important. This is important. Okay, and then down here is our F block. And this is 4 and 5. See, there's no 6 or 7. And then, yeah, you can count. But, so that is kind of little cheat sheet, if you will. Not really cheaty. It's perfectly okay to use it. That just helps you. It makes it go faster. I mean, you probably figured that out during Kahoot today or whenever you did Kahoot. But, okay, that's enough of me rambling. Let's do some other stuff. Okay, so, blah, blah, blah. Down, please. Okay. This is why I don't do things late at night. It's actually only 8 o'clock, but that's not. Okay, I'm going to stop rambling, and I am now going to talk about atomic radii. Because that's important. Yes, it is. Atomic radii. Okay. So, atomic radii indicates the size. I can't remember which way S's go. That's a C. Oh my goodness. Indicates size of neutral atoms. Neutral being the keyword. Also size, because we're doing radius. So, the radius, radii for plural, increases as energy levels are added. That is the word R. So if we go to our little crazy periodic table over here, the way atomic radii are going to go, I should clean this, make a new, I'm going to draw a periodic table because that's a cool one. Okay, periodic table. That doesn't even look right. Okay. That's the periodic table. Okay, so yeah, y'all know I'm not in art. So this is the periodic table. So how atomic radii are going to go is that they're going to increase down groups and they're going to increase going left. So francium down here in the corner has the largest atomic radii, while helium has the smallest. So that's the way the arrows go. And they're increasing along this arrow. And remember, the group is more important than the across. So if you have things in the same, or like you have like, they're in the same, I don't even know what I'm saying. Like they're on top of whatever. If you don't know, go by the group first before you do the period. Left or right, whatever you want to call it. Okay. Now, when we have ions, it's a different story. Because ions, if you remember, have lost or gained electrons. So that is going to change their size, actually, because as they gain or lose electrons, the nucleus's hold on the other electrons is going to change based on having that lost electron. So for cations, these are the positive ones, they're going to be smaller than the neutral atom. And they're going to be smaller because now that the atom has lost electrons, those protons are going to have more of a pull on the ones that are left. They're going to be able to pull them in closer and make that radius smaller. So, say we have calcium ion and we have calcium. The smaller one is going to be the calcium ion because ions are smaller. But say we have anions, they're actually going to be larger than the neutral atom because there's more electrons now, so they're going to spread out more. There's less, the protons have less pull. So say you have chlorine or chlorine, no, negative. The smaller one is your chlorine. Smaller. Because that's the neutral one in that ion, so it's spread out. So, okay, so those are the radii stuff. Now we have ionization energy. I do not like spelling the word energy. It's a weird word. Okay, which can also be abbreviated to IE, not C, IE. Okay, so ionization energy is the energy needed to remove electrons from an atom. So there's different states of electron energy. We're going to make this simple since we're in 10th grade chemistry and just do the first one. So as energy levels are added, the inner energy levels kind of shield the outer electrons from the attraction, from the proton's attraction. I cannot spell anything today. From the proton's attraction, which is also called the shielding effect. So this means that the inner energy levels, the inner electrons are harder to get rid of because they're closer than the other ones. The other ones are kind of just loosey-goosey. Well, not really loosey-goosey. They're still there. But they're really easy to just come by and take. So, ionization energy decreases down groups and increases across periods. So, if I draw my beautiful periodic table again, because I know you all enjoyed the last one a lot, the beautiful artiste. Ta-da! Okay, so these are actually going to go the opposite way of the radii. Going to go up, go this way. So it's going to increase up, and it's going to increase from left to right. Because, I mean, think about it. If you're a francium who has, I don't remember the exact number, but a lot of electrons, it's going to be hard to hold on to all of those. I mean, you know, if you're carrying like 78 balls, you're bound to drop a few that are, you know, at the very top or bottom of your pile. So that's why its IE is really small. But say you're hydrogen with 1, you're going to hold on to that thing pretty tightly because, you know, say you're the noble gases, it's going to take a lot of energy because they're stable, they're full, they really don't like their electrons being taken from them. So they're going to hold on to those things. So that's why you're going to have more energy the farther you get across, because these are already pretty close to being full. It's the same thing with why these over here are cations, they lose electrons, and these are anions, they keep their electron. Because they're closer to 8, they're closer to being 8 once they lose one. Okay, there's one more thing, and it's electron affinity. Affinity is such a fun word. I really like that word. Okay, electron affinity. And that is atoms. Whoops. That's an S. That looks like those things from math. Atoms' tendency to gain electrons, or an atom's attraction for electrons. So it's going to be high for nonmetals because they want that one more electron to be full, and it's going to be low for metals. Except the noble gases. The noble gases are the exception here because they do not want electrons and they are not getting rid of their electrons. They are going to keep them. So the arrows actually go the same way. Minus, remember, noble gas is the exception. Blah, blah. That's a star. Noble gas is the exception. But the arrows are going to go the same way because these are kind of the same concepts, just ionization energy is the quantitative. There's a number to it, while electron's affinity is qualitative. It's kind of like the description. So, yes, I hope half my blabbering made sense to y'all. My brain is going in a lot of directions right now. So, yes, that is it. This video is long again. I apologize. I talked a lot more than I needed to. I hope some of that made sense. Yes, if it didn't, please come ask me questions. I might be able to explain it better in the morning. Yeah, that's it. And, yeah. Okay, bye, y'all.